Thank you very much. And thank you very much for the invitation. I would like to talk about a finiteness result for some special lattices of signature to M. So let L be an even lattice of signature to N, and I assume that N is larger than 2. And I write dl, the Hermitian symmetric domain for L, which by definition is defined as follows. And this space has two components, as you know, and we take connected component. And inside this domain, we have the Heegner divisor defined by -2 vectors in the lattice. So this is the union of hyperplane section defined by -2 vectors in the lattice. Grichenko and Nikulin define two reflective modular forms as modular forms whose zero divisor is set theoretically contained in the special divisor. So a modular form on this domain, and with respect to some subgroup of the orthogonal group and the character, it is said to be too reflective if one and only if the support of the divisor, the divisor of this modular form is contained in the Heegner divisor. And the lattice is said to be too reflective if there exists a too reflective modular form. For some group and character. Of course, I assume that this is non-constant. So the most famous example of such a modular form is Borcherds phi 12 for the even unimodular lattice of type 226. And also Borcherds and Enriquez form of weight 4 for the period lattice of Enriquez surfaces. So this means that the subgroup of the orthogonal group acting trivially on the discriminant group. And also, for example, in dimension 3, it exists theta constants, so product of 10 even theta constants gives an example of such a modular form. So this is a Ziegler modular form for for the symplectic group. But up to projectivity, the symplectic group, this symplectic group is also almost equal to the special orthogonal group of the lattice 2 hyperbolic plane plus A1. So there are some hints that such a modular form. Okay. And so Grichenko-Nikulin more generally defined reflective modular forms as modular forms whose zero divisor is contained in reflective hyperplanes. And some of my results I'm going to talk can be generalized to reflective modular forms. But today I would like to concentrate on the most basic cases, two reflective case. And there are some hints that reflective or two reflective forms are related to exceptional and interesting orthogonal groups. So, for example, originally Grichenko and Nikulin defines this class of modular forms for the construction of Lorentzian-Kac-Moody algebra. And when the lattice is the polarized K3 lattice, in the case of polarized K3 lattice, if we have such a modular form, then it characterizes the discriminant divisor. And also, there's some recent work of Grichenko and Fleck that the existence of some reflective modular forms implies uniruledness of modular form. So for example, if there exists two reflective forms of weight larger than the dimension, and whose zero has no multiple component, so every zero order is 0 or 1, then the modular variety for the stable orthogonal group is uniruled. So as I understand Lorentzian construction of generalized Kac-Moody algebra or uniruledness of the corresponding modular variety. So these properties partly characterize interesting orthogonal group. And there are many overlap between the class of orthogonal groups characterized by these properties. So uniruled or unirational modular varieties, and some interesting Lorentzian Kac-Moody algebras. And I also know a paper of Borcherds who by many examples relate reflective modular forms to hyperbolic reflection group. And it seems that there are some overlap between them. And reflective modular forms or two reflective modular forms so sits around the intersection of these class of orthogonal groups. Now, about
you have a counterexample that they are not in the intersection, or
excuse me.
do you have an example of these two reflexive lattices that are not in the intersection of these two cases?
I'm not sure, but there should be some difference. There should be some. For example, if the modular form has small weight, then the modular variety may not be uniruled. Yeah, I think there are large overlap, but there should be some differences. But I don't know precise picture. Yes. Okay, there's a now conjecture of Gritzenko-Nikuri that the number of two reflective lattices of singulature 2m would be finite. And I'd like to talk that, so this conjecture is true in the range n larger than or equal to 7. And I also gave a concrete bound on n. So namely, there exists no two reflective lattice from dimension greater than 30. In dimension 26, we have Borcherds 512. So this bound 30 will be near the best. Now I have to remark that in the K3, polarized K3 lattice case, the finiteness was first proved by Nikuri, and then also strengthened by Loyenha. And Scheithauer gave a classification of maybe most interesting class of reflective modular forms, so classification of reflective modular forms of singular weight. The most possibly most small weight, and under some condition on the discriminant. Okay, so I will talk about the proof in the rest time. So the proof consists of two steps. The first is, so there are two sentences, but I first proved that no existence in higher dimension. So the range of n is limited, and then I prove the finiteness for each fixed n. And the technique used in these two steps are different. For first step, I use the theory of Borcherds product. And for this finiteness step, I use estimate of volume. Estimate of volume between the modular varieties and the -2 Heegner divisors. So, okay, then before speaking to the actual proof, I also explained the two basic reduction technique. The first is in the definition, I allowed all finite index subgroup of the orthogonal group and all character. But in order to prove non-existence, I can normalize the arithmetic group. So L is too reflective if and only if there exists two reflective form with respect to the stable orthogonal group. So this is because because the order of the character is finite, so we can take some self-product of the modular form to kill the character, and also we can change the arithmetic group freely, also because we can take product of the initial modular form over the difference of two arithmetic groups. And true reflectiveness does not change under this product process. And by using this, I can also prove that if L is too reflective, then any over lattice, finite index over lattice of L is also too reflective. This is because the stable orthogonal group of the lattice is contained in the full orthogonal group of the over lattice. So when proving non-existence in higher dimension, we can restrict to maximal lattices in particular.
But you also get more -2 vectors in L prime.
Yeah, but the zero divisor is the Heegner divisor of L is contained the Heegner divisor of L prime. And and the orbit of the minus vectors in L is still minus vectors in L prime. Yes. This property does not hold for more general reflective lattices.
So the idea is to prove it for the maximal lattice.
Yes, in dimension, in this step, we can use this reduction. Okay, so now the basic object in the study of two reflective forms, I think, will be a cone of two reflective forms, which I'm going to explain now. I assume here that the L contains two hyperbolic planes, which of course applies to maximal lattices in dimension larger than 6 or 7. So under this decomposition, we have the reducible decomposition of the Hegel divisors as follows. So let me denote by H0 be the component of the Hegel divisors defined by the divisibility 1 condition. And let me denote by RL be the subset of the discriminant group of order 2 and norm minus 1 over 2. And for an element of this subset of the discriminant group, so let me denote by H mu be the component of the Hegel divisor defined by this condition, minus 2. And L can be divided by divisibility 2, and L can be divided by in the dual lattice, and in the discriminant group, this is congruent. This gives mu. So this is a little bit long, but so preparing this notation, we have the decomposition of the Hegel divisor. And this is essentially an irreducible decomposition in the level of modular forms. So irreducible decomposition up to the action of the modular group. Now suppose we have two reflective forms. For this normalized arithmetic group. And then its divisor can be written as a combination of these components. So the zero divisor can be written in this form. And writing slightly differently, and this is also beta 0h plus beta mu minus beta 0 h mu. Now, h and h mu are Hegner divisors in the sense of Borcherds. So f is a Borcherds product by the well-known theorem of Brunier. And conversely, by theorem of Borcherds, we can now given such which given multiplicity can be realized as the divisor of modular forms. So application of Borcherds theorem. So first given multiplicity, there exists a two reflective form with this divisor. If and only if and only if, so for any elliptic cusp form, which I write in the Fourier series form, for any, this is for any cusp form, of weight 1 plus n over 2 and value in the value representation of the -1 scaling of L, and we have the linear relation. As follows. So thanks to this criterion, so I define CL to be the cone, the cone in the semigroup of the multiplicity. Cut out, so linearly cut out by the Fourier coefficients of cusp forms of this type of. So I use the space of this. I write the space of such cusp forms usually as follows. And by the Borcherds theorem, this equals to the semigroup. of two reflective forms up to scalar multiplication. Now there is a result of McGraw that this space of cusp forms has a basis with rational Fourier coefficients. So actually, this cone CL are cut out from this original semigroup by finitely many linear functions with rational coefficients. And plus this, if we use so-called Goldan's lemma, which I found in a textbook of convex body or toric geometry, then we see that this cone is finitely generated. So two reflective lattices are finite, but actually if we fix a lattice, then the semigroup of two reflective modular forms after normalizing the arithmetic group are also essentially finite. So essentially two reflective modular forms are also finite. Now let me start the proof of the finiteness theorem. There consists of several steps. Let me first say that two reflective forms is exceptional if it vanishes at the main component, H0 component of the -2 Heegner divisors. So the first step is to prove with no with only condition that the lattice contains two hyperbolic plane, that there exists no exceptional means that the divisor is contained in this splitting in -2 vectors. But for general lattices, RL is empty. It does, generic lattice don't have splitting -2 vectors. So I say exceptional. So the first step is to show that there exists no non-exceptional two reflective forms. In dimension greater than 26. This bound is best possible because in dimension 26, we have Borcherds phi 12. So this is, I think, the proof of this very simple. So let EL be the consider the Eisenstein series of the obstruction type, the value representation of the scaling of -1 scaling of the lattice of type, and weight n over 2 minus 11. And this Eisenstein series converges because of the condition on the dimension. So this is greater than 2, so EL tau converges. And also consider the classical cusp form of weight 12, scalar valued cusp form of weight 12. So take their product, then EL product delta is cusp form.
Sorry.
Yes, yes.
I seem to have missed something very elementary.
Yes.
A reflective form is one which vanishes on the Higner, on all the Higner devices.
Contains, yes. Okay. Okay. So yes, so these coefficients may vary. So consider these modular forms and take their product. So this is a cusp form of type, obstruction type, and weight, the obstruction type, or obstruction weight. And the Fourier expansion of this cusp form is as follows. E0, this is the vector of the group ring of the discriminant form corresponding to 0 element, and Q plus and higher power of Q. Because the constant term of this Eisenstein series is just E0, and the multiplication by delta shifts the coefficients of the Eisenstein series. So now if we have two reflective forms, then its coefficients beta 0 is the pairing of F against this obstruction cusp form. And by this description, this should be 0. So two reflective forms, if exists, must be exceptional. I would like to stress that this delta, this cusp form of weight 12 plays two roles. For Borcherds phi 12. The first is for constructing phi 12. The second is for eliminating modular forms of higher dimension. Now, it remains to show the non-existence of exceptional form. So the second step is to show if there exists two exceptional form for L, then there exists two reflective lattice. Say L prime of one dimension lower and smaller discriminant group. I will not explain the detail of this reduction step, but basically, if we have an exceptional form, it does not vanish at the main component H0. So we can restrict the two reflective forms to a component of this Hegner divisor. Restriction to a component of H0. Which is again two reflective forms. And a component of this is defined by -2 vectors and by the orthogonal complement of the -2 vectors. And its discriminant form is one this bigger than AL, but we can take over lattice. Take over lattice of this of the lattice for this H0, and then if we take over lattice, the discriminant forms get shrinked. So then the final step is to show that there exists no two reflective and maximal lattice in dimension greater than 30. This follows by applying step 2 3 times. So since we are in large dimension, this L prime is this L prime is again exceptional, and we can again use this step. So first, the two since L is maximal, its discriminant form is anisotropic, and of course the two component of is also anisotropic. Don't have any non-zero isotropic element, and in particular, it has length at most 3. And we can use step 2 repeatedly. At most 3 times. Because if we use this step 2 process, then the length of the discriminant form will be decreased. So it can be used at most 3 times. And then the result is say L prime prime prime. So 2 reflective. And 3 times, so the dimension is larger than 27. But then, so we did this process as far as possible. Then this cannot be, I cannot have -2 vectors of splitting type. So this contradicts step 1. Because it must be exceptional type, but cannot be exceptional type because it doesn't have such component. Now it remains to prove the finiteness at the remaining 7 to 26 region. So suppose I introduced a natural invariant of 2 reflective forms. Suppose F is 2 reflective, and write its 0 divisor as before, as this form. And let me denote its weight as alpha. Then take the ratio of alpha and beta and take the maximal. So this is the highest vanishing order relative to the weight. And let me call this tentatively 2 reflective slope of these modular forms. And now, by an application of a volume estimate, which I gave previously, is the following. So let's fix a bound of the slope. Let's say some rational number. Then the number of lattices such that there exist 2 hyperbolic planes, and L has 2 reflective form of this bounded slope is finite. The number of such lattices is finite. I can't explain this in short, but basically, why this is, well, basically, so if we have such a modular form, then the modular forms, the line bundle of modular forms of weight 1 is smaller than lambda Hegner divisor. So in particular, lambda inverse L minus H is not big. And what I proved previously is that if we fix a coefficient of here, then there are only finitely many lattices such that this Q divisor is not big. And yes, there are also, this is an effective. So there's a function on n such that if the determinant of the lattice exceeds this value, then this divisor is always big. So now, admitting this, we are reduced to estimate from above estimate from above the two reflective slope. And the natural idea is to restrict the given modular forms to modular curves, because over modular curves we can use some fundamental results safely as a theory of smooth Riemann surfaces. So let K be an arbitrary sublattice of the given lattice of signature to 1. So if we have an embedding, then the domain, we have an embedding of domain. And this dk, one-dimensional, is naturally isomorphic to the upper half plane, actually, the Segre embedding of the upper half, conic embedding of the upper half plane. So we want to restrict given modular forms to this upper half plane, but of course some non-vanishing condition is required. So assume that this modular curve is not totally contained in the -2 Heegner divisor, and in order to apply some estimate on the modular curves, assume that dk have intersect with the component where f attains its slope. So this is assumption. Then if these conditions are satisfied, the restriction of f to dk is a modular form in one variable on upper half plane with respect to the stable orthogonal group of K, and its weight as a modular form on the upper half plane is twice the weight, or twice its weight as a modular form on the orthogonal symmetric domain. So weight is multiplied, and since this intersects with the component of maximal slope, it has a 0 of order alpha lambda f. Now, by the basic theory of modular forms of one variable, a modular form on upper half plane of fixed weight, say k, and fixed arithmetic group, say gamma, can have only bounded order of 0 in say interior, because this is a section of a line bundle, and this bounded order grows in first order of the weight. So there exists a constant depending only on the lattice, such that the slope of f is bounded by this constant determined by k. So if we have such a generic modular curve, then we obtain a bound of the slope. Then the final step is a very technical lemma that there exists a finite set of within fixed, there is a finite set of lattices of signature 2, 1, such that for any even lattices of signature 2 n, but here arises a technical condition plus a condition. So this condition I can write that the two component of the length of the two component of the discriminant group is smaller than n minus 3, and the odd component has length smaller than this. But this is technical condition. So for any lattice of fixed signature plus such condition, and for any reflective modular forms, two reflective forms, there exists an embedding from some member of this finite pool into the lattice that satisfying the genericity conditions. So satisfying these two conditions. So this gives a finiteness under the conditions. And if n is larger than 7, this condition finally appears here finally appear in this step. If n is larger than or equal to 7, then this condition can be removed by a trick over lattice. So this is the proof of the finiteness at fixed n. So I have finished. Thank you very much.